Greetings everyone, and thank you for attending my IEEE Sensors 2020 talk about our optical fiber tip heat sensor featuring a multi-positional Fabry Perot cavity resonator. I am Jeremiah Williams, a recent graduate of the Air Force Institute of Technology. This work is a direct follow-on to the research conducted by Jonathan Smith with our advisor, Dr. Hengky Chandrahalim, and the direct support of Dr. Joe Suelzer and Dr. Nick Usechak of the Air Force Research Laboratory. Now let's begin.
Today I'm going to talk about the motivation behind our research, the operating principle of this device, the design of our specific device, our fabrication technique, the experiment we performed, the results of that experiment, and some opportunities for future work. So why did we pursue this research in the first place? Well, this whole sensor scheme of a micro Fabry Perot cavity integrated with an optical fiber presents a promising opportunity to lower the size, weight, and power requirements of sensitive systems such as satellites and drones. There's also an opportunity to use this technology to combine several sensors down into a single multi-purpose sensor. We also want to explore the capabilities of this truly amazing two-photon polymerization microfabrication technique that we have access to. More specifically, this work is a follow-on to previous work by our group, and we aim to improve the quality factor of our previous devices with a reflective coating, particularly a reflective coating deposited by directional thin film deposition. This capability in itself presents an opportunity for integrating a multitude of materials for various purposes not limited to reflective coatings. The heart of our device is a ubiquitous optical component, the Fabry Perot resonator. This component consists of two parallel optical surfaces of some partial reflectivity. Light is introduced to the device, and most of this light will reflect off of either surface. Certain wavelengths will undergo multiple internal reflections to constructively interfere with themselves, also known as resonance, within the cavity and transmit out of the cavity. These wavelengths are determined by the distance between the mirrors and the refractive index of the interstitial medium inside the cavity. Multiple wavelengths will resonate in a given cavity and are defined by their mode order. Adding curved optical surfaces to the resonator is known to improve the misalignment sensitivity and walk-off losses suffered by devices with planar mirrors. The reflection intensity output by a Fabry Perot cavity is most often modeled with the Airy distribution, which is included at the top of the page. Differentiating the Airy distribution and taking a linear approximation yields the relationship seen at the bottom of the page, in which small changes to the length of the cavity and the refractive index of the medium inside the cavity produce small changes to the location of the resonant wavelength with a linear relationship. Thus, by monitoring the wavelength at which a Fabry Perot cavity produces resonance, environmental phenomena that affect the length or refractive index of the cavity can be observed. Our device takes advantage of this relationship to measure air temperature, which causes both thermal deformation of the cavity and a shift in the refractive index of the air. We calculate the refractive index of the air at a given temperature with the Sidor technique, although the change in length due to thermal deformation dominates the shift in the resonant wavelength of the cavity. This figure shows a plot of the Airy distribution over our spectrum of interest with some hypothetical shifts in cavity length and a constant refractive index of 1. This helps to visualize the ideal response of our device. This figure plots another important feature of the Fabry Perot resonator, the reflectance of the optical surfaces. Higher reflectances yield a greater extinction ratio, smaller full width at half max, and overall higher quality resonant features. High quality resonant features allow for greater sensitivity, detection limits, and detection ranges, as individual peaks can be monitored with less confusion. This graphic summarizes the operating principle of our temperature sensor. The Fabry Perot cavity is situated on the tip of an optical fiber, which serves as a highly integrated waveguide to introduce light and capture reflections. Most of the light introduced to the resonator by the fiber reflects and is isolated in the experimental setup, while the resonant wavelengths transmit out of the cavity. These wavelengths shift as the temperature of the air causes thermal deformation that alters the cavity length. The supporting posts of the device are constrained against the fiber and can only expand upward to increase the size of the cavity. The hinged mirror is mechanically decoupled from the posts, so the hinged mirror expands in both directions, reducing the size of the cavity. Thus, a change in air temperature produces a high sensitivity optical response. Next, I'm going to discuss the design of our device. Included here are 3 renderings of the device in the partially open, fully open, and closed positions. I'd like to point out some of the general dimensions of the fiber in the cavity, as well as some of the important features of our device. The hinged mirror is latched into place with the latching mechanism and a lip on the mirror. It is rotated on a pin within the pin housing seen at the base of the mirror. It is difficult to see at this angle, but there are 5 1-micron diameter posts that connect the pin of the hinged mirror to the base when it is fabricated, so it is not just floating around in midair. The motivation for this design is to deposit a reflective thin film onto the mirrors of the Fabry Perot cavity to improve the quality of the resonant features. Our previous designs, seen on the left, are static devices. While we can deposit onto their outer surfaces, we eventually desire a 3-mirror device with 2 cavities. Such a device would be self-referencing and multi-purpose, as the enclosed cavity reacts only to deformation, and the open cavity reacts to both deformation and the refractive index of the interstitial medium. Highly conformal techniques, such as atomic layer deposition, are expensive and time-consuming. Thus, the hinge is designed to expose 3 surfaces to directional deposition. Now, we've fabricated our device using two-photon polymerization. This is an additive manufacturing technique, similar to stereolithography 3D printing, in which a photoactive resin is selectively polymerized or solidified with a high-energy laser. Traditionally, this is done with UV light, but the same polymerization energy can be achieved with 2 photons at a higher wavelength. The volume within a laser beam that has sufficient energy for 2-photon polymerization is significantly smaller than the volume capable of single-photon polymerization. Thus, a much smaller voxel, or 3D pixel, can be used to build structures within the resin when using 2-photon polymerization. This technique has already been demonstrated to create some really amazing devices on optical fiber tips, some examples of which are included here. Specifically, we mounted our fiber into a side-loading fiber chuck and loaded it into our 2-photon polymerization system, the Nanoscribe Photonic Professional GT. This mounting process took about 20 minutes. Writing the device took about 10 minutes. You can see some of the layers as it was built up from the face of the fiber. You can see our voxel size there, that is in microns. After the device was written, the fiber was immersed into propylene glycol methyl ether acetate, or SU8 developer, for 20 minutes, and then cleaned off with isopropyl alcohol for 10 minutes. This footage shows the process of breaking the mirror free from its supports with a semiconductor analysis probe and moving it into the open position for reflective film deposition. A gold film was deposited via magnetron sputtering, with the device oriented such that the fiber face was parallel to the sputtering target. The hinged mirror was then lowered into place with the semiconductor analysis probe. The flexibility of the material was relatively forgiving for these manipulations, which required manual dexterity about equal to precise wire bonding. We tested the device with the experimental setup pictured here. The optical circulator, a very useful off-the-shelf optical component, was used to isolate the reflection of the device. A variable wavelength laser was connected to the first port of the circulator, the device fiber was connected to the second port, and a photoreceiver connected to the third port, which output a voltage to an oscilloscope. The device was suspended over a hot plate, and the air temperature was monitored with a thermocouple suspended at the same height. Once the air reached a desired temperature, the laser was activated and swept over a bandwidth of 1460 to 1580 nanometers. The laser exhibited a wavelength-dependent power output, which is subtracted from each measurement. Each reading then shows a voltage proportional to the reflected power over the spectrum introduced by the variable wavelength laser. Measurements are then normalized between 1 and 0. The graphic on the left depicts 3 such measurements, with the area distribution plotted on top of the data for visualization purposes only. The area distribution was not fit to the individual dips because they exhibited a non-ideal asymmetry, as seen in the figure on the right. This shape has been observed in the literature before and may be caused by the scanning speed of the laser or a phase shift introduced by a metal coating near the limited numerical aperture of an optical fiber. While further investigation is needed to fully understand this asymmetry, we fit a version of the skewed Cauchy distribution to 200 points around each dip, which captured the shape of the resonance feature fairly accurately. The central wavelength of the resonant feature is extracted from this fitting and plotted in this figure at each temperature used during the experiment. The vertical and horizontal error bars represent the accuracy of the test setup and fitting and the thermocouple respectively. The dashed line plots the theoretical change in wavelength for the theoretical changes in cavity length due to thermal expansion and refractive index with air temperature. The intercept is chosen arbitrarily to place the line on top of our data, and the coefficient of thermal expansion used for this calculation was derived experimentally in our group's previous work. The shift in resonance we observe follows a linear trend and matches the slope of the predicted shift nicely. A significant degree of hysteresis is present in this data, which we attribute to the mirror resettling after initial expansion into the clearance between the pin and its housing. This would explain the consistency of the offset between the two measurements. Stabilizing the device to remove this clearance is on the top of our list for future work. Our current ideas include locking the pin with an optical adhesive or fabricating a mechanical structure such as a cam or shim to hold the mirror once it is lowered. We also hope to create the aforementioned dual cavity device to sense both temperature and refractive index shifts independently. Additionally, we are working on designs to better align the top mirror when it is lowered by fabricating a full perimeter ledge that it can be dropped onto. Finally, we hope to investigate strategies to house and protect the device, as well as experiments to demonstrate refractive index sensing, pressure sensing, and strain sensing. This concludes my presentation. Thank you all for sticking with me. I'd like to give a special acknowledgement to the project sponsor at AFOSR, the AFRL Materials Directorate staff who helped with the nanoscribe, and the AFIT Cleanroom staff who helped with our thin film sputtering and the space to do these experiments. Everybody stay safe and have a great day. Thank you again.